So we are actually trying to calculate what is the number of times sum equals sum plus j operation. This is addition operation is performed here. Now, outer for loop that is given in step 3, how many times it is repeated? Outer for loop. I square less than or equal to n, we can write it as it is same as I less than or equal to square root of n. No? Is that correct? Now the equation, the for loop given becomes same as for I equal to 1, I less than or equal to square root of n, I plus plus. How many times it is repeated? For each value of I, one time, it is square root of n minus 1 plus 1. This is square root of n times, no? Is there any doubt in outer for loop? Calculating number of times outer for loop is repeated. So that means how many times this operation is performed? Square root of n times. Now, how many times this inner for loop is repeated? How many times it is repeated? We have already calculated, no, for j equal to 1, j less than or equal to say some p, j plus plus. How many times it is j equal to j into 2. How many times this loop is repeated? Is repeated how many times?
n by 2.
Is repeated how many times?
Log p times.
Approximately log p base 2 times, log p base 2 times. Now, instead of p, what is that we have here? What is that we have?
Square.
Square. Instead of p, we have n square. Now, can you tell me how many times it is repeated?
N times, no?
Half log n.
How many times, madam?
N times, no?
So wherever p is there, replace that with n squared. That's all, no? P we replace with n squared. So how many times it is repeated? Log n square, approximately log n square base 2. We know that it is same as? It is same as?
2 log n.
2 log n base 2. So how many times this is repeated? Approximately 2 log n base 2 times. That means how many times this is repeated? This operation is performed. How many times its operation is performed? Square root of n into approximately roughly 2 log n base 2 times. That means what is the order of growth? What is the order of growth of t of n? Order of growth of t of n?
Root n log n.
Root n log n. Thank you, sir. Root n log n. So therefore t of n can be written as big O of root n log n. Is that correct? Can we write it as theta of root n log n? Is this correct or not? This is true anyhow. Is it theta of root n log n? Is it theta of root n log n or not?
No, sir.
It's a correct no. Only approximately means maybe here one time or two times more. No, that much only it happens. So that order of growth there is no change. Still, its order of growth is root n log n only. Once we know that its order of growth is root n log n, Immediately in a second we need to say no whether it is right or wrong. It is correct only. It's a correct only. So now what about this? How many times it's repeated? Or what is T of n value? T of n is number of times sum equals sum plus j operation is performed when n is given as input. What is T of n?
Same as last time.
Here, how many times it is repeated? Square root of n times. This we started in the previous example 1 to n square we increased by increasing it by 2 times every time. But here the other way we are doing n square to 1 we are coming down by reducing it by half every time. Okay, both are same. So that means how many times it is repeated? 2 log n base 2. So overall, what is the order of growth here? It is also root n log n, and it is same again. It can be written as theta of root n log n. Now, please tell me how many times NIT Warangal is printed when n is given as input. Let T of n be the number of times NIT Warangal is printed when n is given as input. Then what is T of n value? Outermost for loop, how many times it is repeated?
N time.
It is clear. Okay, n times. So this is repeated n times. So how many times it is repeated for each value of I? How many times it's repeated for each value of I? When I equal to 1, what are the values j takes?
1 to n square.
1 to n square. 1 to n square. When I equal to 2, what are the values j takes? Still it's
Also,
1 to n square.
Yeah.
And swan, when I equal to n also, what are the values j takes? 1 to n square. Is that okay? Okay, let me write it some like this. I equal to 1. When I equal to 1, what are the value j equal to 1 or j equal to 2 or and so on? J goes up to n square. Is that okay? When I equal to 1, j varies from 1 to n square. When j equal to 1, I equal to 1, j equal to 1, how many times this innermost for loop is repeated? What are the values k takes? When I equal to 1 and j equal to 1, what are the values k takes?
1 times.
1 to 1,
Yes.
that is only 1. When I equal to 1, j equal to 2. I equal to 1, j equal to 2.
2 times.
What are the values k takes?
1 to 2.
1 to 2. When I equal to 1, j equal to 3. 1 to 3. And swan, when I equal to 1, j equal to n square. K equals to 1 to n square. 1 to n square. 1 to n square. If you have any confusion, no, simply we can write it as this operation is performed. This is NIT Warangal is printed for each value of k, from 1 to j one time or not. Is that okay? For each value of k, 1 to j one time it is printed or not? Yes. But this entire operation is performed for for this entire operation is performed for each value of
J vary from 1 to
value
n
of
square.
j, each value of j from 1 to n square. But this entire thing is performed for each value of I, each value of I from each value of I from
1 to n.
1 to n. Now this is T of n over. Now only we need to simplify. Because it is straightforward, only one value incrementation. No, we can nicely get a summation expression like this. We simply get summation expression like this. If it is k equal to k plus 2 or k plus 3, j equal to j by 2, something like that, then directly summation is not possible. No, directly we can write, but still it's somewhat confusing. Okay. So in this case, at least we can write it here. So what is value of this? What is this value? Sigma I equal to 1 to k equal to 1 to j 1. What is this value?
J minus 1.
J minus 1 plus 1.
Yeah,
J
J.
no, sir. It is
J.
J only. It is J. Now what is sigma j equal to 1 to n square j? We have this now. We have I equal to 1 to n. This we have T of n is this. What now we can simplify this now. What is this value? What is that?
And into n plus 1 into 2n plus 1 by 6.
So it is nothing but j equal to 1 to n square. 1 plus 2 plus 3 plus n square. No. Okay, let me write here. Sigma j equal to 1 to n square. It is same as 1 plus j equal to 1 n square into n square plus 1 by 2. Thank you. So it is 1 plus 2 plus and so on n square. So it is n square into n square plus 1 by 2. Is that correct? Is that correct? Okay. So we can replace this with, therefore, what is T of n? Equal to sigma I equals to 1 to n square into n square plus 1 by 2. Now what is T of n? Now again, this entire thing we can write it as T of n, we can write it as 1 by 2 sigma I equal to 1 to n 1 by 2 outside n power 4 plus n square. Is that okay? Is that correct? Is that correct? Now 1 by 2 is independent of I. We can take it outside. It is sigma I equals to 1 to n n power 4 plus n square. This again we can apply sigma to each of the terms separately. No. I equal to 1 to n power 4 plus I equal to 1 to n square. So 1 by 2 if I take common, what is this value? Sigma I equal to 1 to n power 4. What is this value? N power 4 is independent of I. We can take it outside. What is that value? What is sigma I equal to 1 to n power 4? 1. Oh, sorry. Sigma I equals to 1 to n power 4.
N power 5.
So n power 4 we can take it outside. So it is sigma I equal to 1 to n 1. This value we know that it is n. So total it is n power 5 now. Similarly, what is sigma I equal to 1 to n square? What is sigma I equal to 1 to n square?
N power 3, sir.
N power 3. So finally 1 by 2 if we take common, n power 5 plus n power 3 we get now T of n. What is the order of growth of T of n?
N power 5.
N power 5. Thank you. N power 5. So therefore T of n is, can we write it as theta of n power 5? T of n is theta of n power 5. We write it as theta of n power 5. This is correct. Okay. Why? Because its order of growth is n power 5. Like this, we can have many nested for loops, no? Even 4 or 5, it doesn't matter. Okay, it doesn't matter. Okay, you can practice more examples. Okay. Next, we move on to. Okay, it's the same thing. Next, we move on to how to analyze recursive algorithms. How to analyze recursive algorithms. What in order to analyze running time of recursive algorithms, we follow the same procedure which we have followed for analyzing non-recursive or iterative algorithms. Okay, so in that non-recursive or iterative algorithm, what's the first step? We need to decide on parameter indicating input size. Here also same thing. We need to decide on which parameter we take it as input size parameter. Next, what is most important operation in the algorithm? That is basic operation we need to identify. We need to identify. What is the next most important step? Similar to non-recursive case, whether the number of times basic operation is repeated, it only depends on input size or actual values in the input also. That is input instance that we need to determine. Next, this is only the change. So here, in case of non-recursive, every time T of n, we have got some summation expression, no sigma, something like that. Okay, no, we have got a summation expression, but here we get a recurrence relation. When n is input size, T of n is number of times that particular operation is repeated. But T of n will get something like T of n minus 1 plus something, or T of n minus 1 plus T of n minus 2 plus something. Like that, a recurrence relation we get. After that, what is next step? There, whatever in case of non-recursive, whatever summation expression we got, we simplified it. Here also we need to solve that recurrence relation. We need to solve its recurrence relation and find out what is solution to that recurrence relation. Once we know what is solution to that recurrence relation, automatically we can find out what is order of growth of T of n. After finding order of growth, we can represent it using some asymptotic notation. Okay. Let us see with an example. So all of you remember now what's a recurrence relation? For example, if we are given a sequence, so this is 10, 12, 14, 16, 18 like this. Okay. This is a sequence. This we can call it as 0th term in the sequence. This is first term. This is second term. This is third term, and so on like this. So A0 equal to 0, we can say A1 equal to 1, A1 equal to A0 equal 10, A1 equal to 12, A2 equal to 14, like this. Now, what is AN? What is AN? AN, in this case, we can easily represent A1 is of the form A0 plus 2 form. Is that correct? What is A2? A1 plus 2 form. Similarly, A3 equals 16. It is of the form A2 plus 2. So is there relation between a number and an element and its previous element? There is nice relationship, no? 12 is 10 plus 2, 14 is 12 plus 2, 16 is 14 plus 2. That means here AN we can represent it as simply AN minus 1 plus 2. an minus 1 plus 2. Is that okay? An minus 1 plus 2. Or if we want, we can consider it as a first term also. This is first term, this is second term, third term, fourth term, like that. Then an we can call it as nth term in the sequence. An we can call it as nth term in the sequence. Okay, it is n. So we are able to represent nth term in the sequence in terms of sum of its previous terms. In terms of sum of its previous terms, like this. Sum of its previous terms. Sum of its previous terms. Then this type of equation or relation, this we call it as recurrence relation. Recurrence relation. Even here also, here we can represent an as an minus 1 plus 1. Is that correct? In example 2. Example 3 also we can represent an as an minus 1 plus 1. Now whether these two recurrence relations are same, does it mean that two recurrence relations are same? The corresponding sequences are same. Does it mean that the corresponding sequences are same?
Yes, sir.
No, they are not same. No. Here it is starting from 10, 11, 12, 13 like this. Here it is 20, 21, 22, 23 like this. Both are different sequences, no?
Only initial values are different, right?
So then how to uniquely define that sequence? How to uniquely define that sequence? For example, I want sequence given in example 2, that only. For that, if I clearly say that an is an minus 1 plus 1 and a naught, if we start with a naught, otherwise a1, whatever. A naught is, say, in second case it is 10. Here it is greater than or equal to 1. Is it uniquely defines that sequence or not? We can do it this way, or an minus 1 plus 1 for all n greater than or equal to 2, and a1 is 10. This is also correct, no? Is that correct?
Yes, sir.
Both are same. Okay, no? Both are the same. This way we can define. We can define it like this also. Okay. So this is a recurrence relation which uniquely identifies or defines this sequence given in example 2. Example 2. Now you tell me what is the recurrence relation for this is called recurrence. This is a recurrence relation. No, what is this is called initial condition. This is called initial condition. Initial condition. If the initial condition changes, whether the recurrence relation, the actual sequence changes or not. If the initial condition is different, whether we get a different sequence or not.
Yes, sir, we get a different sequence.
We get a different sequence. Though the general form is same, if initial condition is different, we get entirely different sequence. Now, in case of example 3, what is the difference? An can be written as an minus 1 plus 1 for all, say, n greater than or equal to 2, and a1 is 20. Now both are entirely different, no? This is defined sequence given in example 3. Is that okay? Okay. So we have general term we are representing in terms of sum of its previous terms. Sum means not SUM, it is SOME, sum of its previous terms. Here we represent in terms of only one of its previous term. It can be two of its previous terms. For example, if I take Fibonacci sequence, no, all of you are familiar with this 3, 5, 8. Here we can represent an as
an minus 1 plus an minus 2. 2.
Okay.
Yes, sir.
An minus 1 plus an minus 2.
Minus
Here
2.
we are representing in terms of two of its previous terms. We are representing in terms of two of its previous terms. Is that okay? So it need not be addition. It can be even subtraction also. Okay, it can be subtraction. So that means here we need to give initial condition to uniquely identify that sequence or to define that sequence. That initial condition is important. Now you tell me how many initial conditions we need to give? if my recurrence relation is like this, an is an minus 1 plus 2 times an minus 2 plus an minus 3. How many recurrence relation, how many initial conditions do we need to give in this case? How many initial conditions do we need to give?
3,
Three.
sir.
3. Number of initial conditions. Number of initial conditions is 3. For example, an is an minus 1 plus an minus 4. Here, how many initial conditions should be given?
4, sir.
It is 4. It is 4, not 2. It is not based on number of terms here. Number of terms here. Okay, no, it is not based on number of previous terms here. It is the gap between an and the smallest term which is present here. Smallest term is an minus 4. Gap is 4. So that means 4 initial conditions should be given. So n minus 4 is 4. And so 4 initial conditions should be given. Is that okay? Is that clear? What is reconciliation and the number of initial conditions? Okay. Now consider this simple algorithm. What does this algorithm do? What does this algorithm do?
Factorial.
A factorial of a non-negative integer. We know that 0 factorial is 1 and n factorial is n into factorial of n minus 1. Okay. Now you tell me what is input size parameter here? Parameter indicating input size.
N.
Okay. We can say it as n. We can say it as n only. Okay, I'll elaborate on this maybe after some classes. Okay. Now, what is most important operation in this algorithm? Basic operation.
Multiplication.
So this operation we can consider it as most important operation. No, that is multiplication.
Yes, sir.
Now, what is next step? Let T of n be the what is T of n? Number of multiplications performed. Number of multiplications performed when n is given as input. Correct now? When n is input, let T of n number of multiplications performed and n is input. Now, whether this T of n value, it only depends on n or actual values in the input also. Here, this question itself is meaningless. Why? Because whatever we are considering as input size, that itself is our given number, no? Unlike linear search where input size is n, values are different. Here, whatever we are given, no, that itself we are considering it as input size, no? Is the point clear? Is it clear?
Yes, sir.
If n equals 5, how many times this operation is performed? So in order to calculate 5 factorial, it first calculates
5 into
4 factorial. In order to calculate 4 factorial, it
3
calculates
factorial,
3 factorial, 2
2
factorial,
factorial,
1 factorial. Next 0 factorial, directly we get answer as 1. Then it substitutes back. Okay, it goes like this, no? It goes like this. So now how many times this multiplication operation is performed? Here 1 into 1 is performed. That is 1. Here
2 into 1. Then 3 into 2. Then
is 2
4 into
factorial.
6. Yeah.
Okay. Here it is
4 into 6.
3 factorial value. Here you can say this is 2 factorial value. This is 1 factorial value. Okay. Next, this is 5 into 4 factorial value. No? Is that okay? Now, how many times this multiplication operation is performed?
5 times.
5 times. If n equals 6 is given, 6 times. N equals 7, 7 times. So that means it depends on n only, no? Depends on
N
n.
factorial.
So do we have best case, worst case, average case here?
No, sir.
No, no such cases. Let T of n be the number of times it is for. Now, how? What is T of n value? Let when in this entire algorithm, when n is given as input, number of times or basic operation, that is multiplication is performed is T of n, when n is given as input. Now, how many times this operation is performed?
N minus 1 into n.
Because here one multiplication we are performing, one multiplication plus, in order to perform this, how many multiplications are required? How many, in order to calculate factorial of n minus 1, how many multiplications are required?
N minus 1.
No. See,
n
in order to
multiplications.
find factorial of n, the number of multiplications required is T of n. In order to calculate factorial of n, number of multiplications required is T of n. In order to calculate factorial of n minus 1, how many multiplications are required?
T of n minus 1.
T of n minus 1. Now, in order to calculate T of n, this value we need to calculate, and this is one additional multiplication we need to perform. Now you tell me, can you represent T of n in terms of previous values? In terms of its previous values?
T of n minus 1 plus 1.
T of n minus 1 plus 1. Is it clear to everyone? T of n value, because this is simple algorithm, directly we are saying n minus 1. But actually, in factorial of n, number of times multiplication is performed. If I denote it by T of n, for factorial of n minus 1, it will be T of n minus 1. Number of multiplications performed is number of multiplications performed in order to calculate factorial of n minus 1 plus this is the additional multiplication which we are performing here. So T of n can be written as T of n minus 1 plus 1. When is it true? When n value is whatever value we supply, that is always say greater than. N value is
Greater than 1. Greater than 1. Greater than equal to 1.
Greater than or equal to 1. Now we need to give initial condition. No, what is initial condition? What is initial condition?
T of n equal to 1 if n equal to 0.
So T of 0, we can write it as 0.
No, we can write, okay, in case of multiplication, we can write 0. Yeah, that's fine.
Is that correct?
Yeah, correct.
T of 0 equal to 0.
Yes.
Is there any doubt? Okay. Now, what is our next thing that we need to do? Here, is it a recurrence relation? Yes, it's a recurrence relation. Now we need to know how to solve this recurrence relations. How to solve recurrence relations. But our intention now is it, are we really interested in solving recurrence relation, or what is that we are interested in? We just wanted to find order of growth of T of n. Whether we are able to get it without solving or by solving, that is different issue. Somehow we should get correct order of growth of T of n. Correct order of growth of T of n. So how to get order of growth of T of n? This we can solve this recurrence relation, no? We can solve this recurrence relation. How to solve this recurrence relation? This is simple recurrence relation. Now, what is the method that we can use here?
Substitution method.
Substitution method we can use. So it is of the form T of n is T of n minus 1 plus 1. But what is T of n minus 1? Do we know this value? What is T of n minus 1? Do we know that?
T of n minus 2 plus 1.
We don't. So that's why wherever n is there, you substitute n minus 1. What is that we get? What is that we get? What is T of n minus 1? What is T of n minus 1? What is T of n minus 1?
T of n minus 2 plus 1.
T of n minus 2 plus 1. Already plus 1 is there. Already plus 1 is there. We write it like this. Is that okay? Already plus 1. But what is T of n minus 2? Do we know that? Wherever n is there, you substitute n minus 2. in T of n equal to n minus 1 plus 1, wherever n is there, n minus 2. What is that we get? T of n minus 2 is, T of n minus 2 is, T of n minus 2 is,
T of n minus 3 plus 1.
everyone, are you following? T of n minus 3 plus 1, already plus 1 is there. What is T of n minus 3? Wherever n is there, n minus 3. What is T of n minus 3?
T of n minus 4 plus 1.
T of n minus 4 plus 1. Already this is plus 1 plus 1 plus 1 is there. I have written like this. But what is the use of substituting like this? Even if I substitute 100 times, what is that we get after 100 times? T of n minus 100 plus n minus 100 plus
100.
Because 100 ones, no? Here 4 means 4 ones we have, 3 means 3 ones we have, 2 means 2 ones, 1 means 1. There is a pattern, nice pattern. So plus 1 plus 1 plus 1 like this 100 times. But what is the use? Even if I substitute T of n minus 1 crore, T of n minus 1 crore, after 1 crore times T of n minus 1 crore plus 1 crore we get. But we don't know what is the value of T of n minus 1 crore, T of n minus 1 crore. So what is the value that we know? Only T of 0. If we get 0 here, we know what to substitute. Otherwise, we don't know anything about the value of that. Okay. Now, after I iterations, what is that we get? After I iterations, what is that we get? What is that we get? After I iterations, this I can, in general, I can write it at T of n minus I plus I. Is that correct? After I iterations, it is T of n minus I plus I.
Yes.
But what is the use? Again, n minus I, we don't know. But we know only value of T of 0. When does n minus I become 0?
When I is n.
I equal to n. So at I equal to n, what happens? At I equal to n, at I equals to n, what happens? What is T of n? T of n
0.
minus, in place of I, we are substituting n. N minus n plus n. Is that okay? So what is this value? T of 0 plus n. What is T of 0? It is already given here. T of 0 is 0. 0 plus n. So therefore it is n. It is n. So fourth step over. So finally represent it using order of growth of n is n. Order of growth of T of n is n. So therefore, what is T of n? T of n can be written as theta of n. Theta of n. Is this correct? Is this correct? Here only difference is we get a reconciliation. We should know how to solve that reconciliation. This method is called backward substitution method, no? Backward substitution, no? This method, no? There are different ways of solving reconciliation. Substitution method, characteristic equation or characteristic roots method, generating functions method. Substitution. We should know how to solve reconciliations. This is substitution method. The only difference is we get a reconciliation. After that, everything is same, except the fourth step. You please, all of you, see this. Is that okay? Is it okay? Those who haven't understood, you please see this.
Yes.
Is it clear to everyone?
Yes, sir.
Okay, okay. So next problem that we consider is towers of Hanoi problem. So all of you must be knowing, what is tower of Hanoi problem? It is also called Tower of Brahma or Lucas Tower. Why? Because there is origin in India, that is in Varanasi, Kasi, that Kasi Vishwanathan temple. So it is below there are the 3 pillars where poles, okay, where there are 64 golden discs, and the people, people, they are moving disc from one pole to other pole according to rules of Brahma. Okay, rules of Brahma. What are rules means? These are the rules given here. Okay, and it is believed that once it transform disc, move disc from one pole to other pole, then world comes to end, it seems. World comes to end. This is another version of the problem. That's why it is also called Tower of Brahma. Tower of Brahma. So what are rules here? We are given 3 poles from source to destination, source, auxiliary, destination. We need to transfer disk from one pole to other pole according to the rules. What are the rules? Only one disk can be moved at a time. Okay. In each move, only top disk we need to move. Only top disk we need to move. What is the other important rule? No smaller disk should be on top of larger disk. Always, okay, no smaller disks. Sorry, it is the other way. Okay, no larger disk may be placed on top of smaller disk. Smaller disk. Now, what is the goal here? We need to transfer this disk from one pole to other pole using according to the rules, using
Auxiliary.
minimum number of moves. Using auxiliary, but with minimum number of moves.
Yes.
Okay, is it possible? So if there is, this is source, this is auxiliary, this is destination. If there is only one disk, how many moves are required? If
One
there is
move.
only one disk,
One move.
only one move, no, source to destination we move. If there
Yes.
are 2 disks, like this,
3 moves.
so what is that we do first? What is that we do first?
Lower one will be on auxiliary.
So first step
Smaller one,
that
yeah.
we do is
Lower one will be moved to the destination.
first one we move
Move to the destination.
we move from one disk, we move from source to source to
Auxiliary.
source,
Auxiliary.
Auxiliary.
source to
Destination.
auxiliary with the help of destination. No? One disk move from source to auxiliary with the help of destination. That means what is the is this correct? Is it correct?
Yes, sir.
Middle one is auxiliary one. Okay, source to auxiliary we are moving with the help of this destination. So this becomes auxiliary now. Okay, now this becomes auxiliary. What is the next thing that we do? Second step, what is that we do? Step 2.
So
Whatever disk, whichever disk is there on auxiliary, okay, no, that auxiliary, okay, sorry, auxiliary, that disk we move from auxiliary to
Destination.
yes, auxiliary to destination. So auxiliary to destination with the help of source, that whether we use it or not different, auxiliary to destination. That means what are most, so this is moved from here to D. So this is smallest one, this is larger one. Is that correct? What is the next thing that we do in step 3? What is step 3 we do? whichever disk is there on no, it is correct.
Second is wrong, sir.
So no, source,
Ah.
this is source to destination.
Source to
no?
destination.
This is source to destination. Okay, this is whatever we
Yes.
diagram is correct, but whatever we have written is wrong. This is from source to
Destination.
source to destination with the help of
Auxiliary.
partner. Next,
Mm.
next auxiliary, whatever
Auxiliary.
is there, this one we move from auxiliary to destination with the help of source.
Source.
Okay, so that means after third step, what is the state? All are
Moved.
source, auxiliary, destination. Is that okay? Is that okay? So
Yes,
n
sir.
equal to 2, we have 3 moves. In general, if we are given some n disks, how do we do this? Source has n disks. This is auxiliary, this is destination.
2 to the power of n minus 1.
1, sir.
Bottom n minus 1, we group into 1. This is a, oh, sorry. This is not. Top n minus 1. Top n minus 1, we consider this is a bottom disk. So whatever steps we followed here to move 2 disks from source to destination, same steps we follow. So that means what is that we do? What is that we do? Source to destination, source to destination, source to destination, source to auxiliary via destination. We move how many disks?
N minus 1.
recursively. N minus 1
Yes, sir.
recursively. After that, what is that we do? After that, what is that we do? After that, what is that we do? The largest disk, we move from source to destination, 1 disk, largest disk. Is that okay? Next step. What is the state? State is here. It is largest is there. Here, n minus 1 are there. It is like this. After this second step, it is like this. Here n minus 1. This is largest here. After this, now whatever is there in our auxiliary, this we move from
Auxiliary to destination.
auxiliary to destination with the help of source.
Source.
How many? N minus 1. Now all will be here.
Mm.
N minus 1. Is that okay? So now,
Yes,
what
sir.
is the algorithm? Simple. Recursive algorithm is easy, no? We are given n disks. Recursively, we move top n minus 1 disk, from one pole to other pole. Then the largest disk, the disk which is present on source, that we directly move from source to destination. Next, again, those n minus 1 top disk, we move from one pole to other pole. The other pole means that is finally destination pole recursively. Based on this simple algorithm, we can write. So if n equal to 1, do we need to do anything? Directly we can move. No? Directly move from source to destination. Directly move from source to destination. Okay. So now based on this, we can easily write a recursive algorithm. No? If n equal to 1, move directly from source to destination. Otherwise, these 3 steps we follow. Otherwise, these 3 steps we have to follow. I show that. Okay. See, if n equal to 1, move disk directly from source to destination. Is that okay? Otherwise, this recursively, whatever we discuss, that we do. That we do. So our main intention here is, if we are given n disks, the number of moves we require, that let us call it as T of n. When we are given n disks, number of moves that we call it as T of n. Now you tell me what is T of 1? What is input size here? What is input size? What is input size?
Number of disks.
That is n. Okay.
Mm.
What is basic operation?
Move operation.
Basic operation is move operation. Moving a disk. Moving a disk. Next. Let T of n be the number of moves. Number of moves given n disks. Now, whether T of n value, it only depends on n or actual values also. The actual values here, it is meaningless, no? So directly it depends on only on n. N. So now what is T of n? What is T of n? Clearly, we know that T of 1 is 1. Is that correct? Based on this condition, if I equal to 1, move this. Based on this, we know that T of 1 is 1. Otherwise,
T of 2 equal to
if n is greater than or equal to 2, if n is greater than or equal to 2, then what is that? We need to perform this operation. How many moves we require in this case? It is a recursive call. It's a recursive call. For n disks,
T of n minus
number of moves is T of n. For n minus 1 disks, number of moves will be
T of n minus 1.
T of n minus 1. Here, how many moves we are making here? One move.
One
directly.
move.
So this is again how many?
Tn minus 1.
So now what is total number of moves? If n is greater than or equal to 2,
2 times Tn minus 1.
T of n minus 1 plus 1 plus T of n minus 1. T of n minus 1 plus 1 plus T of n minus 1. T of n is 2 times T of n minus 1 plus 1. Now again we need to solve this. We need to solve it. So if you what is the answer that we get?
2 power n
minus 1. 2 power n minus 1.
Yes.
So therefore, what is order of growth? 2 power
2
n.
power
So
n.
T of n can be written as theta of 2 power n. Is that okay? How to solve it? Okay, now how to solve it? Again, same procedure we follow. Same procedure we follow, that is substitution method. Substitution method. T of n is 2 times T of n minus 1 plus 1. Okay, again, write T of n is 2 times T of n minus 1 plus 1. Now tell me what is T of n minus 1? Wherever n is there, you substitute n minus 1. What is T of n minus 1? N is there, n minus 1. N minus 1 minus 1 plus 1. So what is T of n minus 1? What is T of n minus 1?
Twice T of n minus 2.
2 times T of n minus 2 plus 1. No? So similarly, what is T of n minus 2? Wherever T is there, n is there, n minus 2.
T of n minus 2
times
plus
T of n minus 2 minus 1 plus 1. What is, similarly, tell me what is T of n minus 3? 2 times
n minus 3 plus, oh sorry,
Is that
minus
okay?
1.
We keep doing like this. Okay. Now what is, now we don't know what is value of this. T of n minus 1, we can substitute to 2 times T of n minus 2 plus 1. This we can substitute now. So 2 is already there. One more 2 times T of n minus 2 plus 1. Already plus 1 is there. This we can write it as 2 into 2, 2 squared. T of n minus 2 plus 2 plus 1. Is that okay? Now what is T of n minus 2? What is
T
T
of
of n
minus
minus 2? This is same as
T of
2 times T of n minus 3 plus 1. So in place of that, we can write that now.
yes.
2 times T of n minus 3 plus 1 plus 2 plus 1. So it is same as 2 keep t of n minus 3 plus 2 square plus 2 plus 1. But what is t of n minus 3?
Again 2t of n minus 4 plus 1.
2 times t of n minus 4 plus 1. So it is 2 keep. In place of t of n minus 3, we are substituting t of n minus 4 plus 1. Plus already 2 square 2, it is there. 2 square plus 2 plus 1. So it is same as 2 power 4 t of n minus 4 plus 2 keep plus 2 square plus 2 plus 1. Now if you observe here, now we can see some common pattern. Here, if 2 square is there, we here 2 means here also we have 2. Here we have up to 2 power 1. 2 power 1. Here if 3 is there, here also we have 3. Here we have up to 3 minus 1. That is 2. Here if there is 4 means, there also we have 4. There also if 4 means, here also it is 4. Here we have up to 4 minus 1. These values are, this we can consider as 2 power 0, 2 power 1 like this. This is 2 power 0, 2 power 1 like this, no? Correct. Now what is the common pattern? After I steps,
2 power I.
2 power I, t of n minus I plus 2 power
I minus 1.
I minus 1 plus 2 power I minus 2 plus and so on up to 1. Up to 1. 1 means this is 2 power
0.
2 power 0. But we don't know what is t of n minus I know. We only know the value of
T of 1.
we only know t of 1 equal to 1. But if we get 1 here, we know what to substitute. So that means when do we get 1 here? N minus 1, 1 means, that means what? I equal to n minus 1, no? I equal to n minus. So at I equal to n minus 1, at I equal to n minus 1, what is t of n? What is t of n?
2 power n minus 1.
2 power n minus 1 into t of n minus 1 plus 2 power n minus 1 minus 1 plus 2 power n minus 1 minus 2 plus and so on plus 2 power 1 plus 2 power 0. Is that okay? So this is same as 2 power n minus 1 into t of 1 plus 2 power n minus 2 plus 2 power n minus 3 plus and so on 2 power 1 plus 2 power 0. What is t of 1? What is t of 1? It is given to us, no? It is as 1. This value is 1. So this becomes
2 power n minus
1 plus 2 power n minus 2 plus 2 power n minus 3 plus
and so on.
2 power 1 plus 2 power 0, which is same as 1 plus 2 plus 2 square plus and so on 2 power n minus 1. It is GP, no? A into r power n minus 1 by r minus 1, no? Okay, what is first term? 1. What is r value? 2 minus 1 by 2 minus 1. Sum of n terms in GP, no? This is the formula, no? Sum of n terms in GP. A into r power n minus 1 by r minus 1. R is common ratio. A is A plus AR correct, no? So this becomes 2 power n minus 1. So therefore T of n is 2 power n minus 1. So what is recurrence for towers of an eye? Running time?
2 power n minus 1.
T of n is 2 times T of n minus 1 plus 1. So n greater than or equal to 2 and T of 1 is 1. Okay. Therefore T of n can be represented as theta of or big O of 2 power n. Exactly we know that it is 2 power n, then why to put it as big O? we can represent like this. Okay. I stop here. Okay.
Sir?
Madam.